Right, hello and welcome. So this is going to be the part two of the introductory lecture to group theory. So we have already stressed at the beginning of the first lecture that group theory is very important for all of uh, theoretical physics. It's how we uh, make concrete how we're going to use symmetries in a system. Okay, so for example, if we need to understand, so given a particular symmetry, there is going to be a symmetry group associated with it. We saw this last time around, that this group structure emerges from the symmetries. And we also saw last time around the case of classical mechanics, where you're looking at Noether's theorem, where every symmetry is every sort of continuous symmetry is going to be linked with a conservation law and a conserved charge. Okay, so let's do this. Let's try and get back to what we were saying, and let me start to share screen now. All right. So I am actually hoping that this lecture is not going to be too long. So yeah, so we were saying again, let me just, okay, let me also reiterate that these lecture notes will be up, and you should be able to see them on the web page very soon. As soon as I upload this lecture onto YouTube, I shall also upload the notes. All right, very good. So as we said, this was, the mathematical structure of a group of symmetry arises in a natural way when we look at systems. So, symmetry, as we were saying before, is mappings of physical states uh, of a system, which leaves the dynamics of the system invariant. And then there are some observations about these mappings that can be made that essentially give us this group structure. So that was what we learned last time around, and we were looking at this continuous parameter, and we were looking at this, and we were looking at what we called local one parameter groups, whereby we are looking at a continuous sort of parametrization of group elements. And what we stressed on is really required is not so it's required that these two group elements, gamma t1 and gamma t2, satisfy this closure relation, and this group sort of so and it is not required that you actually know gamma t for all values of t. You only need to sort of understand how you know uh, so an infinitesimal symmetry, as we were trying to emphasize, will only describe the derivative of gamma t at t equal to 0. And this is it's not necessary to know gamma t at all, for all values of t. It's not even necessary that gamma t be defined for all values of t. All that you require is gamma t obeys this particular law. I mean Sort of group group composition law, if you wish. This is a function where gamma t1 times gamma t2 gives you gamma t1 plus t2. Okay, so this is what is going to be called a local one parameter group. And what it says is that physical, if this is all that is required to understand symmetries, then we do not need to understand the full structure of the group. We can do with things around around the identity element. So that is what is called the algebra, and we are going to make this distinction as we go ahead. We learn this much more. But yeah, so let's see this. So physical systems, it's more important that you're looking at local stuff, so you're actually more interested in the algebras than in the groups in most things. Yeah, so let's go. I mean, again, this is reiterating what we did last time around, and I showed you, this sort of more formal way of trying to understand uh, Noether's theorem, where this symmetries give rise to, I mean, conservation laws and conserve charges. We did this, and we found, we looked at our favorite example of translation. I urge you to actually sit down and work this out just to make sure that you are fine with the steps that we have done in between. So it just shows, Noether theorem shows that, if you have this differentiable family of symmetry, symmetry transformations, this yields I mean, conservation law and a corresponding conserved charge, right? Translational invariance, as we saw in the example, leads to, conservation of momentum. This is something that you guys know very well. Rotational invariance, on the other hand, again, something that you guys know, leads to, the conservation of angular momentum. Okay. I said a little bit about charges not being Noetherian. That's not very important right away. Okay. So now what I want to stress on is Noether's theorem in particular can be applied to any group of, continuous group of symmetries, okay? But you remember that for what we did, again, we use this local one parameter family of symmetries. So these conserved charges that we have defined are related to the infinitesimal symmetries and hence to the algebra and not so much to the group. Okay, so the group. What's the difference between an algebra and the group? As you can understand, what is something that's defined locally and something that's defined globally, if you wish. The algebras and groups are related by, as I say here, as some sort of an exponential mapping. But it's not clear that any local family of symmetries can be integrated to a group by this exponentiation. So it's not. I mean, it's all of these things you would not be able to exponentiate them. For the examples that we will be doing later in the course, we would have the algebra and the group, but this is something that you need to keep in mind. And they actually can be symmetries that are described by algebras alone, and these imply, additional, uh, I mean, uh, conservation laws. There are examples, some things that you guys may have heard of before, something called supersymmetry, which relates bosons with fermions and so on. And there's also the very fun case of, conformal symmetry in 2 dimensions, which, if you are interested in, I have a whole course that I gave last time around. So for those who are interested, you can look into that. So this was classical mechanics. That's still stuff that you guys know well. And this was, again, in the Lagrangian way. So let's quickly understand what happens when you actually are going to the, Hamiltonian description. This is rather interesting. So let me sort of emphasize this. So what happens in the Hamiltonian framework? In the Hamiltonian framework, as you know, all information is actually encoded in the Hamiltonian of a system, which now is going to be the function of positions qi and momentum pi, okay? And the space which is spanned by these pi's and qi's is called phase space. And you need to distinguish this from the, sort of, configuration space, which is the space spanned by only the q's, where the Lagrangian is. Okay, so the Lagrangian and the dynamics of the Lagrangian takes place in the configuration space. Now you have moved to something called phase space, which is the Hamiltonian, which is sort of governed by the Hamiltonian of the system. And this is labeled by pi's and qi's, okay? So for example, if you have a ball and which is moving in 3 dimensions, your position space will be 3-dimensional, x1, x2, x3, right? But when you are moving to the space in which your Hamiltonian is, you will have to there will be PIs for each of them. So so there were three QIs here. There'll be three PIs and three QIs. So it'll become 6-dimensional. Okay. All right. So as you know, again, well, that the equations of motion take this form. These are the Hamiltonian equations. And for systems that can have a both Lagrangian description and Hamiltonian description, you can go between one and the other by writing down H in terms of L. This is a Legendre transform. Okay, so this is something again that you are familiar with. But let me stress on a subtle point out here. This is the for systems which can be treated in both ways. It's not necessary that you can actually have Lagrangian and Hamiltonian descriptions for each thing. Okay. Again, for most examples that we know, for most examples that we will do, it is going to be true, but sometimes it's not the case. Okay, so now, sorry, yeah, I think that was it for this page. Yes. So one of the fundamental fundamental tools of this Hamiltonian formulation is something called a Poisson bracket. Again, I hope you guys know this. So what does a Poisson bracket do? The Poisson bracket is a map. Okay, is a map. I mean, this maps any pair of functions f and g of these are differentiable functions of the dynamical variables p and q. The map this it goes to a single thing. Okay, so this is what the Poisson bracket is, and two functions f and g. It's defined by this guy here. So it's del f del p into sorry, there should be a q here. So let me make sure that I get this corrected. This is a q. So it's a del f del p into del g del q minus del f del p del g del p. Let del f del q uh, del f del q del g del p. So this is the Poisson bracket. So let me maybe sort of mark this out. Uh-oh. All right, so this is not having the desired effect here. That's probably a little better, but anyway, so that's the Poisson Poisson bracket. The important thing for here is to notice that there has this characteristic properties. So if you have something that's lambda and mu are sort of constants, and you have lambda f plus mu g, and you have this other function h, then it just becomes lambda into f of h plus mu into g of h. Okay, so that's by linearity. You also have anti-symmetry, which is obvious from the way that you have actually defined this. So the Poisson bracket of fg is anti-symmetric, and it's minus of the Poisson bracket of gf. The other and very important property that this particular bracket does follow, is something called the Jacobi identity, which is going to be very, very important for us going forward. So this particular triple bracket actually becomes equal to 0. So you should remember that these are in order. So if you order them 1, 2, 3, then you see this is 2, 3, 1. This is sorry, 1, 2, 3, 2, 3, 1, 3, 1, 2. So you see these are all in order. Okay, so cyclic permutations will just get you here. These three properties can be summarized by saying that this Poisson bracket actually turns this space of functions P and Q into a Lie algebra. Okay, this is something that is somewhat deep here, but once you go back and learn, it'll make more sense as we go ahead. But it's very clear that this particular space of functions of P and Q, this becomes a Lie algebra. Now, suppose if you had a Hamiltonian that did not explicitly depend on time, then you could look at the time derivative of any function on a trajectory like this, and if that's a solution to the equations of motion, then you can write it as d dt of f is equal to Poisson bracket of h with f. I am sure that most of you know this, but if not, I'd urge you to just sit down and work this out. Okay. So you just need to figure out what DDT is, break it up, and then you should be able to figure out what this means. Use equations of motion, of course. Now you notice that if h and f Poisson commute, then ddt of f is equal to 0, and f becomes a conserved quantity. This has more implications as we go on to say a little shortly. Now, if you have two such functions, f and g, then you'll see that not only an f and g, conserved quantities, but the Poisson bracket of f and g is also another, conserved quantity. So the space of functions that now describes these that describes these conserved quantities closes under the Poisson bracket. It itself becomes a Lie algebra. Okay, and this is a subspace for the space of all functions. So hence, if you want to learn more about conserved charges of a system that are described by a classical Hamiltonian mechanics, as I write here, it's very necessary to investigate the structure of Lie algebras. Okay, and so this, as I was trying to stress before, the Jacobi identity plays a very, very crucial role out here. So this is the one that actually ensures that if f and g are conserved quantities, the Poisson bracket of f and g is also conserved. Okay, as I write here, it's a crucial and non-trivial input for required for having the structure of a Lie algebra. So given a Lie algebra, the generators of a Lie algebra have to actually satisfy this particular identity all the time. So this is how you sort of this is one of the defining features of a Lie algebra. We will understand this as we go on. Now, some more fun things for you to just hear about. So if you have these presence of conserved charges in the system, this puts a very severe constraints on the dynamics of a system. So as I write here, the trajectory that fulfills the equations of motion remains inside a subspace of the phase space in which every conserved quantity takes a fixed value. If you have a 2n, if in a 2n dimensional phase space, there are n such quantities which all Poisson commute. These, typically form an n-dimensional torus. So again, this is a little more advanced than you'd want to go. But the message that you want to take home from this part is that for understanding Hamiltonian mechanics, it's very important to understand Lie algebras. Okay, this of course has not been stressed to you before, but I mean, a part of growing up, if you wish, is trying to, is seeing that many things that you're going to, I mean, that you had learned before, you can learn in new light. So this is something else. Okay, so that was classical mechanics. And now the other thing that a lot of you are familiar with, quantum mechanics. So what does what do the algebras are? Group theory in particular, um, you know, Lie groups and Lie algebras in yeah. What do these have to do with quantum mechanics? So what we know is if you take a system, if you take a classical system, how do you quantize it? So we start off, so if we are looking at this in the Hamiltonian formulation in the sort of canonical way, then you start off with the Poisson brackets of the system and you sort of, I mean, elevate them to, I mean, what we call, I mean, commutator brackets, right? So, and there is a crucial IH cross in front of this, where this A and B are actually given by so this is the anticommutator. Now, so what happens? What is very clear again is that the property is that characterize the Poisson brackets. Those same ones will actually also come to determine come to I mean come to characterize this sort of commutator bracket that you have out here. So again, what we can do is we can summarize this by the statement that this bracket that we've written down endows the space of linear functions of the Hilbert space with the structure of a Lie algebra. Okay. Now remember that if you are in the Heisenberg picture, the physical states, which are the elements of the Hilbert space, don't depend on time, but the observables do. And their time dependence is given by ddt of at is equal to IH cross H of A. And again, what you see is if you have H with A equal to 0, then these lead to this leads to A being conserved, and this is what I write down out here: observables that lead to conservation laws commute with the Hamiltonian. And just like earlier, by uh, Jacobi identity, what we will see is that these again close to form a subalgebra. Okay, so if there is something which is, for example, uh, H of A is equal to 0 and H of B is equal to 0, we'll find H of AB equal to 0. Okay, this is something that you can sit and just do. Okay, very good. So these were sort of, again, so you understand again what we do. What it's very crucial again that Lie algebras will be crucial to understanding what quantum mechanics now has to say. Okay, so we have seen that there's a very significant role in classical mechanics. Now we are seeing that there's an equivalently significant role when we come to quantum mechanics. Okay, there are other sorts of symmetry that you may have encountered. So there's something called gate symmetry, which you have encountered in electrodynamics. These are also things that you will encounter when you are looking at the weak electric force and the strong electric force and so on. And there are also other fun things called, for example, called duality symmetries. So this is sort of if you if you have a sort of class of theories A, B, C, D in some way, and these are these a priori look very, I mean, dissimilar from each other, but under a certain mapping, maybe this is the theory A maps to the theory C, and the theory B maps to the theory D. So if you have things like that, for example, something where you have very strong, very strong coupling, if that particular coupling is replaced by the inverse of it, maybe one of the theories maps to the other, then that is going to be something like a weak, strong weak duality. So there would be, so two apparently unrelated theories can be related to each other by these uh, sort of mappings. So these are called, duality symmetries. We would not have a lot to say about this, but these are very, very interesting things as well. So at the end of the day, let's sort of have a set of points that you can take home if you wish. You guys are all home, so not much point in saying take home, but bad jokes aside, so the point is that if you are looking at symmetries in physical systems, this naturally leads to the structure of groups in the algebras. Okay, we have looked at Noether's theorem, and we have seen how in a Lagrangian setting, this yields conservation laws. Interestingly enough, applying Noether's theorem doesn't require the whole group structure. It just requires you to look at the local one parameter group of symmetries. Hence, it's not really the group that is so important. It's more the infinitesimal version of symmetries around the identity, which is going to be called the algebra. These are, so the take-home message from here is that as you will go forward, we will learn that the algebras will be more of importance than groups in these sort of particular ways that we want to build up fundamental theories. What we saw earlier in this class today is, you can have equivalent descriptions, as for example, in classical mechanics, in the Hamiltonian framework. So in the Hamiltonian framework, what I reminded you is that the conserved quantities are actually described by functions in phase space that also commute with the Hamiltonian. We saw that this again is the fact that there is these properties of the Poisson bracket, the properties like like the Jacobi identity, for example, leads to its being very intimately related to Lie algebras and so on. So this will be linked up to things that are called symplectic groups. Maybe we can speak about this near the end of the course at some point of time. But again, just to reiterate this, the thing that we set out here is here, right? So the Poisson bracket turns this space of functions P and Q into a Lie algebra. So that's what we saw there. And ultimately, we saw that there is a very similar sort of description that you can do also for quantum mechanics. And again, what we saw that there the Poisson bracket goes on to this usual. So this goes to IH cross times the usual commutator bracket, which again has the same properties that characterize the Poisson bracket. And again, we can summarize a statement by saying that this commutator bracket endows the space of linear functions, linear operators of the Hilbert space with the structure of a Lie algebra. Okay, so this is important. Yeah. Uh, and again, so you have the similar, I mean, things that we said earlier about, what would be the symmetry. So the observables that lead to, I mean, conservation laws are going to be the ones for which, the commutator with the Hamiltonian becomes equal to zero. So this is how this is related to the symmetries in the quantum mechanical setup. So that was the idea for the class today, and I will not belabor this point anymore. But it's very apparent for us now that it's very, very important for us to try and understand and try to build up the blocks of group theory, and from their Lie groups and Lie algebras, which are the things that we really want to be looking at. So I mean, uh, continuous groups and how to deal with that. But before we go there, we want to be looking at finite groups. So we will be starting off with discrete groups in the next class, and so yeah, I think that's about it for the class for for now. And I hope to be sharing something again very soon. Okay. And again, yeah, so the lecture notes will also go online along with this. All right, very good. Thank you. And let's sort of stop the share. And okay, so I will see you guys in the next lecture. Bye bye for now.